Hi, welcome to the Libre-SOC series of videos on the design architecture. This particular video is going to be on the level 0 cache buffer design, which is capable of merging multiple loads or stores together that occur in from parallel multiple elements, and keeps the level 1 cache line requests full without corrupting memory. First thing to notice is that we're not doing total store.store order, so consequently the loads are separated from in batches from stores. Stores are separated in batches from loads, and atomic requests are likewise separated. Beyond that, as long as there's no data corruption, the order in which a batch of loads can be done is completely independent. If the individual loads within the thing is in any order, and the individual order of the stores, as long as there is no address clashes, and also be completely independent in any order. Atomic requests will do one at a time. So the high level is that we have a single level 0 buffer with twin level 1 caches. One of them deals with the even address numbers where address bit 4 is 0, and the other one's for odd where address bit 4 is 1. Other than that, ignore the lines in between here. We have 8 function units, load store computational units as they're called, and it's critical to note that unlike a pipelined design, these function units do not let go of their requests. They do not hand over responsibility for store load or hand over responsibility for store. They sit here, they hand out their request, they wait for acknowledgement until it is completed, and that goes back into the directive. That information goes back into the directed acyclic graph, which monitors the read and write dependencies. In this case, particular case, we have normally you'd have for ALU operations, you would have a function unit registered FU reg dependent matrices which has the register numbers in here and the function unit number coming in here, augmented by a function unit to function unit one, which this basically maintains a directed acyclic graph of the order between the function units. And this pair of things is critical because this one can only do function unit to register information about what reads and what writes are required, whereas this one it stores critical information about the results. So the pair gives you a DAG of the register dependencies per function unit maintaining that information. In this case, this needs to be backed up by for memory. A similar thing needs to be done. So you have a memory function unit one, which corresponds again to the function unit res one, which does exactly the same job, but we have to have a function unit to function unit ordering system, and that's what I think. This is background, by the way. We'll get onto what the actual level 0 cache buffer does as well, but it's important to appreciate the constraints and of what the previous matrices satisfy, such that the level 0 cache buffer does not need to deal with them. All right. So there's an address match system here, which all it does is it matches bits 4 through 11 and it may catch some additional things. So basically, let's say that you have two addresses where in bits 4 through 11 there is a match. The bits 4 through 11. There's no point really in going to check the additional bits above that. So this is quite interesting. You end up with some things which, if you did additional checks on the upper bits, you would find out that they didn't match. But to be honest, it's 0.01% of all of load store conflicts, and it's not worth the effort. So we don't bother until later. But that's another story. We'll come on to that in a minute. So the first thing is that this matrix here checks the interdependencies between loads and stores. So you get a sequence that stores the sequence. Basically, it uses a matrix to store a linked list. So each of these cells represents one instance. Each of these cells represents one instance of the load store ordering, and it only goes on if this one goes on if there's a write after read. That one goes on if there's a read after write, and consequently, it records that the instructions before it were a load, or the instructions before it were a store. So if it's a store, it must block on loads, and if it's a load, it must block on stores. So consequently, this system provides us with a means to completely isolate batches of loads from batches of stores and from batches of, single entry batches of atomic operations. So let's constraint number one. So that the loads level 0 cache buffer does not need to deal with anything other than a batch of loads or a batch of loads. It will not ever receive a sequence of mixed loads and stores. The second thing is, thanks to the address matching system, is that it will never receive a batch of in that batch of loads or that batch of stores. There will never be an overlapping address, and that's clear. That's not so important for loads, except for I/O loads, of course. Okay, which are treated as atomic. Loads, it's not so important, but for stores, you absolutely cannot have something which goes into store into address 0, address 1, and store into address 2 if they are byte address 2. If they are 8 bytes long, they're going to overlap. But if they were address 1 and address 9, they would not. So that's the responsibility of that map matrix. Now, it turns out that by only checking bits 4 through 11, there are opportunities where this things are missed. So if we have a couple of 16-byte things here. So 7. By only checking those bits, you could actually have something where you've got a load from here and a load from here, and another one with a load from here. This is bits 0 to 3, 3 of the address, 0 to 3 of the address. So there's 16 entries in here. By only checking bits 4 through 11, we miss opportunities to merge these through, so that could actually go into the same level 1 cache line here. That could go into the same level 1 cache line, and that could go in the same level cache line as a single request like that. Or maybe let's say make that one 2. These are bytes and this is a half word. So that opportunity to merge all those is missed in a single level 1 cache line. To fix that, what we do is we turn the load and the store into a byte mask. So if you have 1248 gets turned into a mask, one bit long, 2 bits long, 4 bits long, or 8 bits long. That then gets shifted up by the address bits 0 to 3. And so consequently we'll end up with a 24-bit mask. Any of those bits will be set. Actually, only 23 because if the bit 16 is set and you've shifted everything into the top 24 bits, actually you can that's a completely new cache line. You can shift it down. Yeah. So it'd be subtle, but ignore that. So basically, we can divide it into a cache line 1 where it's aligned on a 60-bit binary, and you can divide into cache line 2, right? Where when it comes to loading, we can shift and mask and put those back in and merge them back into the single 16 into the data, right? Shift and mask and all of them together, all right? But it's critical to note that when doing this split of these misaligned addresses, the cache line 1 byte address line 4 could be 1, but the misaligned bit covering the rest of the data, that could be a 0. But if this one is the lower bit of the 16-byte cache line is 1, then the upper bit of the misaligned address will be 1. So we know for a fact that this is mutually exclusive of 0, 1 in the cache line 1, cache line 2 requests, right? And that becomes critically important to note later on. So, in particular, we know that when it comes, this is why when we have a level 1 even, this is critically why we have a level 1 0, level 1 even and level 1 odd, because one of the parts of the split request will go into one of these, and the other one we guarantee will go into the opposite one. And for that particular line, the remainder of the bits of the address will be the same. Okay? Right? So consequently, that's why eventually went to this diagram here. Okay. Make sure that's in the middle. Yep, it is. Good. All right. So here's your function units 1, 2, 3, 4, 5, 6, 7, 8. All right, for number 0 to 7. Remember, at no time will they simply hand over a request and expect arbitrarily that it will be completed. It is not a pipeline. It is not a queue. All right. So they will require acknowledgement of that the load or store has absolutely been done before they will drop their request and go back and say to the administrative system, yes, we can proceed with another instruction can be issued. All right. So each one here has they split that the length and the address into a pair. Potentially, almost certainly this one, except for misaligned address requests, which we're assuming are not going to be very common, this one will be run mostly empty, right? So, however, if it does, then the request will be split into two halves. We will identify here through a crossbar, not a blocking multiplexer, a crossbar, because address 4 can be used to either put address bit 4 puts either the one, because of the characteristics of the misaligned address, the address bit 4 will be mutually exclusively set between the two. So one of them will go into this one, and one of them is guaranteed to go into the other one. And so what we can do is, for each of these here, drop address bits 12 to 48 into here. So F bits 12 to 48 here go to there. It's just wires. It's not multiplexed at all. Again, wires to here. Again, wires to here. And the same for address 5 through 11. All right. That gets routed through to here as well. So ignore that, okay? Yeah, actually ignore that one as well. It's exactly the same. All right. Because it's bit 4 is implicitly encoded in whether it's the even or the odd one. All right. So we drop these byte masks, and for each one you route the byte mask. So the only multiplexing that has to be done is a 2 in, 2 out crossbar from either one of them will go the address bit based on address bit 4. One will go to there and one will go to there for each of those. But it's not here to function unit 0 data goes to 1, 2, 3, 4, 5, 6, 7. Its function unit data only goes to function unit data's row. Okay, and the corresponding byte mask, which is the bitmap representing address bits 0 to 3, will be set in here. All right. So on each clock cycle, a priority picker identifies in here and in here, and these are independent. By this time, they're completely independent. Okay, so identifies in here one of these rows. It does not matter which one, so consequently you can use a priority picker. Remember, it doesn't matter because only loads will be in here or only stores, and we are not using a total store order. We're using a weak memory model. So the order in which the loads occur, or in the order in which the individual stores occur, does not matter. And additionally, thanks to the address matching matrices which we ran before, even the stores overlapping you will not have any overlapping stores either. So by this point, we know that nothing in here will overlap. So the only thing we need to do is to pick a row, then check that bits 12 to 48 match, and from these 5 to 11 has already been done by the address matcher, so that information can be carried over from the other matrix, the one that had the what's it called? Oh, what's the name of the thing? The address matching from 5 to 11. So that information of those comparisons has already been done, so we do not need to do it again. Right? So do a priority picker on this, and then for whichever row is picked, all rows below that, we compare bits 12 to 48 and take into account whether the address match information from 5 to 11, which had already been done, also matches. So in effect, we're comparing all of bits 5 through 48 in this row, but we're not doing it twice because half of that work has already been done. All right? And for everything where the address matches in this line, we simply OR out the byte masks, and that corresponds to the byte enable line for that level one cache request. And it doesn't really correspond to byte enable. It corresponds to when we back here, when we've actually got the data, we use that mask to decide which bits are going to be shifted and merged back into the thing. Okay, so that's basically it. And this diagram here from there is a replacement for that, where previously I'd done it as separate level 0 buffers here. Now it's been merged into a one where this is effectively the same and thing. Now, the address bits 12 to 48, if they were not the same back at the split stage, that indicates a page boundary misaligned request, and it can be detected by the fact that address bits 5 through 11 are all ones, because when you add 1 to that to give the misaligned address, it's going to roll over to 0. Those are not going to be the same, and the address 12 to 48 is going to be 1 different. If that happens, we throw in an exception. We are not covering that case. So we are specifically set, and it's okay. I've checked the power specification. It's actually allowed. It's allowed. This is specifically allowed to throw that a misaligned page fault on the high bits. So that case doesn't have to be dealt with. It's a simple OR and detection. When these the augmentation that we did to Mitch Alsop's address matcher matrix was to detect the overlap on these byte masks. So again, we have the address match matrix, which detects on 5 bits 5 through 11. This is Pascal's triangle of address matching. But I augmented it to include checking those bytes as well. So if there is any overlap in these, say there was one that had this bit thing set as well, this one would not be included. Only those two would be included in the address matching. So we're using binary comparison for the bits 4 to 11, but we are using unary comparison of byte masks for bits 0 to 3. Okay. So consequently, back here, by the time it gets to here, we know that there are going to be no conflicts, because that's already been taken care of by the hybrid combination of binary and unary address matching. So that basically allows us to merge 100% hit rate. Any loads and stores, even if we get a sequence of element strided function units load stores, they will be detected here with 100% success rate and merged. Now, one other small detail, which I don't think it would be a good idea to try and implement. I mean, if we've got time, yes, fantastic. But what we want to do is, when you have a vector operation and you know it is element strided, we know at the issue phase that the address is going to be sequential, and consequently the probability that the address 5 to 11 in a sequence of operations being the same is going to be quite high, and it's definitely going to be quite high that bits 12 to 48 will be the same, particularly if they're just a sequence of elements going like this. So what I would like to do is to augment the system so that instead of just bits 12 to 48 and bits 5 to 11, we actually pass through a indication that actually function unit 2's bits 5 to 11 are identical to those of function unit bits 1 and 0. And likewise, that function unit bits 2's address 12 to 48 are identical to 1 and 0, etc., etc. And what's fascinating is that because you're using a counter at the back of when you're doing the element strided address computation, you're using a counter. The only information that you need to detect of whether the address has rolled over is you need bit 5 and you need bit 12, and that's it. If bit 5 changes, you know that the address rolled over, and it will be different here. And if you get to 11111 and it rolls over on here, only bit 12 will change. So you do not need, when we do that optimization of when we add in the vector unit, vector engine, vector issue system, rather than having to compare every single bit 5 through 11 and every single bit 12 to 48, all we need will be address bit 5 and address bit 12. But we'll do that as an optimization later. Okay? All right. So I think that basically covers everything. This diagram, remember that this merge thingy replaces that where you've got bits 12 to 48 there, you've got 4 to 11 as well. Those are the same, and then 4, 0, 1 more thing on that. All right. Then it's a 128-bit data path from here because it's a 16-byte cache line going to a standard level 1 cache, but you have an odd and even one. Here is where we need a wishbone, which will take those 128-bit requests and split them out into 64-bit wishbone requests, one for that and one for that one. So there'll be pairs here. Whether that's twin wishbones, it doesn't really matter. We have a thing. Now, what's very interesting is that if we're passing through the byte lines, the byte enable lines, it's actually the split comes here and here. So if all of the byte lines are 0, byte request lines are 0 here, you don't even need to make the second request. If all those lines are 0 on that one, you don't need to make that request either. So if any of those lines are 1 here or any of these lines are 1, then you need to make 2 requests. And that was why we need 128 to 64-bit arbitration at that point. Very straightforward. Thank you very much.